Generic embeddings completely fail on specialized domains. Look at this 5.85% accuracy on medical data. That is essentially random. Today we are fixing that. In the next 8 minutes, you will fine-tune your own embedding model using Unsloth, completely free on Google Colab. Accuracy went from 5.85% to 77.4%. MR more than doubled. NDCG nearly doubled. And it only took 30 training steps. Let us get into it. If you want to understand what these metrics actually mean and why they matter for your RAG system, I break all of that down in my community. Link in the description. Alright, let us start with why this matters. So why does this matter? When you are building RAG systems, your retrieval quality is everything. Bad retrieval means bad answers. It does not matter how good your LM is. Problem: most embedding models are trained on general web data. They do not understand your domain. Here is a simple example. The headlines Google launches Pixel 10 and Alibaba releases QN4 might be embedded as very similar. They are both tech news. But if you are doing semantic search, they are about completely different things. Fine-tuning aligns the model with your data and your definition of similarity. That is what makes retrieval actually work. Unsloth just added support for embedding model fine-tuning, and it is impressive. You are looking at 1.8 to 3.3 times faster training compared to standard sentence transformers with flash attention. 20% less memory usage. EmbeddingGemma 300M works on just 3 GB of RAM. And the best part, you can export your model anywhere. Transformers, LangChain, Olama, VLLM, Llama.cpp. No lock-in. They support all the popular models. EmbeddingGemma, Qwen3 embedding, BGE, Mini LM, Modern BART. Pretty much anything you would want to use. Standard setup, we are installing Unsloth and the dependencies. This takes about a minute on Colab. Now the key part. We are using fast sentence transformer. This is Unsloth's optimized class for embedding models. We are loading EmbeddingGemma 300M, setting max sequence length to 1024, and using LoRA instead of full fine-tuning. There it is, model loaded on a Tesla T4, which is the free Colab GPU. You can see it is using float 32 precision. Next, we add LoRa adapters. This is the efficiency trick. Instead of training all 300 million parameters, we are only training about 13 million. That is roughly 4% of the model. Rank 32. Targeting the attention and MLP layers. Standard setup. Now our model is ready for training. For training data, we are using a medical dataset, 4.4 million question, passage pairs from biomedical literature. We are streaming just 10,000 training samples and 2,000 for evaluation. That is enough to see real improvements. Here is what a sample looks like. We have a medical question and the passage that answers it. The model learns to embed these closer together in vector space. This is the core of contrastive learning for embeddings. Make relevant pairs similar, push irrelevant pairs apart. Before we train, let us see how the base model performs on this medical data. We are using the information retrieval evaluator from sentence transformers. It tests, given a query, can the model find the right document? Look at these baseline numbers. Accuracy at 1, only 5.85%. That means the correct document is the top result less than 6% of the time. MRR 0.33. It takes a while to find the first relevant result. NDCG 0.43. Overall ranking quality is mediocre. This is a general purpose embedding model trying to understand specialized medical text. It is struggling. Let us see what fine-tuning can do. Training setup. We are using multiple negatives ranking loss. This is the standard loss for embedding fine-tuning. It uses other samples in the batch as negative examples. Batch size 64, gradient accumulation of 2, learning rate 2e minus 5. And importantly, we are only doing 30 steps. This is a quick demo, but you would typically train for a full epoch. Watch the loss it is dropping with each step. 46 minutes of training. Peak memory, about 11 gigs. That is well within the free Colab T4's 15 gig limit. Training is done. Let us see if it actually helped. Moment of truth. Look at this transformation. Accuracy at 1 went from 5.85% to 77.4%. That is a 13 times improvement. MR 0.33 to 0.84 more than doubled. NDCG 0.43 to 0.86 nearly doubled. In just 30 training steps, the model went from basically failing to actually understanding medical text. And here is it working in practice. Medical query about chest pain. The model correctly identifies acute pericarditis as the top match with a 0.70 similarity score. The other conditions are ranked appropriately below. That is the power of domain-specific fine-tuning. For deployment, you have got options. Save the LoRA adapters, save the merged model, export to gguf for llama.cpp or llama. All the standard Unsloth export paths work. So that is how you fine-tune embedding models with Unsloth. You saw those numbers go up. But here is the thing, what do those metrics actually mean? When should you care about MRR versus NDCG? What is actually happening inside that loss function? And what do you do when you run this on your data and the metrics do not improve? That is what I cover in my community. Inside, you will get a full breakdown of every retrieval metric, what they measure when each one matters, a deep dive on the loss function, and how contrastive learning actually works. The annotated notebook with detailed comments on every code block, and a debugging guide for when things do not work as expected. I am opening this up to founding members right now. If you found this useful, hit subscribe for more practical AI tutorials. Thanks for watching, and I will see you in the next one.